So, ladies and gentlemen, welcome back. This particular video is going to focus specifically on rotational kinematics. All right, so if you weren't able to make it to the live Zoom class today, this video is going to cover what we discussed. And what it's going to be is it's going to talk a little bit about the idea of what rotational kinematics is, how we go from linear to rotational kinematics, and how we can use the stuff that we've learned in normal kinematics for rotating systems as well. Okay, so the key to this is actually going to be posted on Canvas. If you go to Canvas, you'll find my key. My key is slightly out of order, so just giving you a heads up, but I'm still going to go through and kind of talk about how to solve these different problems as we go through the notes. All right, so we start with hopefully the fact that you watched the previous video that talked a little bit about all the different types of rotational motion, all the quantities that are involved, and how they're basically just kind of twins to linear motion, all right, with the slight change. So let's get started by looking just at this chart that talks about the things in linear kinematics and the things in rotational kinematics. So in linear kinematics, we know that there are 5 variables that we care about, all right, and we know that it's initial velocity, final velocity, acceleration, displacement, and time. Now in rotational kinematics, which remember are just for things that are turning, rotating, orbiting, they're all involving some sort of rotation. The variables are exactly the same, except you just put the word angular in front of them. So instead of it being initial velocity, it's initial angular velocity, which is how fast the object is spinning. Final velocity, final angular velocity. All right. The symbol for angular velocity is an omega. It's that little curly W here. And usually we measure it in radians per second. Then you have angular acceleration, which is basically just the equivalent of acceleration. The symbol is an alpha, or you can draw as a little fish. Basically, looks like that. But basically, its units are going to be radians per second squared. Then you have normal displacement, and you have angular displacement. Still mean the same thing. Angular displacement just measures the number of radians you've turned in a certain amount of time, or the number of degrees, depending on how you use it. And what we're going to find out is that time is still the same. Time never cares about what's going on. It keeps moving forward. In this case, it's exactly the same. Now, we're going to find out that these two things are related, that the linear quantities and rotational quantities are related in a very specific way. All right, and usually how it works is that the linear velocity, I apologize, didn't mean to put the little dot there. Linear velocity is basically related to angular velocity by this relationship, which is that the angular velocity, how fast I'm spinning, times the radius of the circle that I'm kind of spinning in, is going to equal the linear velocity. All right, and that's something that first can seem kind of weird to kind of imagine, but really what that means is that if I had someone who was on the edge of a merry-go-round at a playground, and it was spinning and spinning and spinning, and that person got thrown off, that linear velocity would be how fast would they start moving forward if they got thrown off that rotating merry-go-round. Okay, and you notice the other ones kind of follow the same path. So for acceleration, linear acceleration is just equal to the angular acceleration times the radius of the circle. And displacement, the linear displacement, something that would be literally how far it goes around the circle, is just equal to the number of radians times the radius of the circle. All right, and we're going to practice using those a little bit later on. So if you're looking at those saying, I don't really understand how those relate, don't worry, we're going to keep practicing it. Okay, now, just like linear kinematics, rotational kinematics also has some equations that govern how it acts and we can use to predict the motion of something. Now, what's interesting, what's kind of useful is that literally it's a straight switch. So all of the linear formulas look exactly the same for rotational motion. All the symbols are just curlier. Because what we've done is we've taken every linear symbol and replaced it with its angular version. All right. Now, looking at these sort of things, they look a little bit different than what we're used to, and that's just because the thing I copied and pasted didn't have things like, VI, VF. But you can kind of imagine that this omega right here, this would be the final angular velocity. Omega naught, it's the initial. Usually we have those little thetas. Usually we would see it as delta theta or delta x for the linear thing. So if you see that, don't get too caught up on what's going on here. It's looking just like we're used to. Okay? Now, of course, just like everything else, if we are using kinematics, whether it is linear or rotational, we're going to have to organize our thoughts in a very specific way. And for us, the way we do that in kinematics is we draw a chart. And rotational kinematics is exactly the same thing. You're going to draw a chart as well. And the best way to show it is to practice it. So right here for question 1, that's exactly what we're going to do. So I'm going to work through question 1 as an example, kind of show us how to go through it. Then we're kind of do this thing where hopefully you pause the video, you kind of work through the questions, unpause it, see how you did, and go from there. All right? So for this first question, I have a blender, and it's off right now. I haven't turned it on. It's already connected to a circuit. Wonder why that circuit's off. Interesting. Now, I turn the blender on, so it starts to turn. And eventually, in about 1.2 seconds, so pretty quickly, it reaches an angular velocity that's spinning speed of 150 radians per second. Now, my first question is, I want to know what is the angular acceleration experienced by the blades? Okay. Now, at first, that's going to be kind of annoying and kind of confusing because it's like, I just don't, what do you mean? What am I looking for? What's this word angular mean? Honestly, all angular means is turning. So the idea that I know a velocity, I know a time, I know an acceleration means that I can fill out a kinematics chart just like linear motion. Okay? Now, this really, really well-drawn kinematics chart going to look something like this. So we have the starting velocity, final velocity, the angular acceleration, time, and delta theta, how many radians it's gone through. Okay? Now, we start by looking at what we know, just like we do for normal kinematics. And in this case, I know that it starts from rest, so omega I is 0. Omega F, the final angular velocity it gets to, is going to be 150. And I know that it takes about 1.2 seconds to do that, so the time is 1.2. And right there, just like linear kinematics, congratulations, you now know 3 things. And if I know 3 things, I can solve for a 4th. So in this case, I want to know angular acceleration. That's this alpha. I know the starting angular velocity, the final angular velocity, and time. Remember, that's 1.2. So the best formula is probably going to be the first one right here. So it would be omega F equals omega I plus alpha t. Okay? And then right there, fill in what we know. We know this is 150. I know omega I is 0. I don't know alpha is what I'm looking for. And I know time is 1.2 seconds. So with that being said, if you kind of move some stuff around, solve for alpha, you'll get that the angular acceleration for this particular question should be 125 radians per second squared. 125 radians per second squared. All right. And right there, literally all we did was the same stuff we've done with kinematics before. The same setup, we draw a chart, we look for what we know, we solve for what we want to find. Okay? The only difference now is it's just for things that are turning, and those symbols all represent just quantities for things that are turning. Okay? Now, part A wants us to find the acceleration. Part B is asking something slightly different. So it says, how many revolutions do the blades make in those 1.2 seconds? Now, usually when we talk about rotational motion in everyday life, we actually talk more about revolutions than we do about the pure just number of degrees and number of radians that I go around. Like if I was talking to someone and said, oh yeah, I went on this ride that goes, I went on this merry-go-round and it went around, I covered 3,000 degrees. Wouldn't make a ton of sense. But if I said, oh yeah, I went around 8 times before the ride stopped, that would make much more sense to who you're talking to. So in this case, we're going to use that idea to solve for the number of revolutions the blade makes in 1.2 seconds. So we're trying to calculate how many times does that blade go around in that amount of time. Okay? Which means the first thing we probably need to find is just how many radians in total I cover, because that's kind of measuring how much I go around in that certain amount of time. So that means I want to find delta theta. So first I want to solve for delta theta. All right? And I know multiple things for this. So I think I can solve for it pretty easily. I know, honestly, acceleration, all these things, so I can pick any of the things up here to find it. So it's really up to you which formula you want to use. I will probably be picking the second formula. But what I want you to do, please, actually, is I want you to pause the video here, solve for delta theta. All right? Solve for it, tell me what it is, and come back to me. Well, I guess tell it to your laptop, and I'll act like I heard it. And then come back. All right? So pause the video here, figure out what delta theta is. Right? So hopefully you had a chance to kind of go through and find delta theta. There are several different ways to do it. One way you can do it is just do the second equation up there on the top of the screen, where I've got delta theta is 1/2 the final velocity plus the initial velocity, or initial minus final. It could be written either way. All right, times the time. So I know the final velocity is 150, starting velocity is 0, the time is 1.2 seconds. Multiply that 1/2. You'll get that delta theta, the amount of radians, and it's going to be radians, not degrees, because the velocity is in radians per second, is going to be 90 radians. So in total, it turns 90 radians. All right. Now, that's not super useful to us, but we can take that 90 radians and turn it into the number of revolutions pretty easily. And how we do that is we think about how many radians I cover in one full revolution. All right. And we know, hopefully remember that in a full circle is 360 degrees, or in radians, it is 2 pi. So to calculate the number of revolutions, what we do is we take the number of radians I traveled. So we're just doing number of revs. Okay. It's going to equal delta theta divided, in this case, it's going to be divided by the amount of radians I do in one revolution. So this will be divided by 2 pi. All right. So the number of revolutions is going to be 90 divided by 2 pi, which means when you do that, you'll get that the number of revolutions is going to be 14.3 revolutions. All right. And we're going to find out in a little bit why that's a particularly useful calculation, because it's going to make our lives very easy for certain calculations that we run into when maybe we're trying to figure out how far something travels while it's rolling. All right. Now, the last piece of this particular side of the sheet is this question. What is the tangential velocity of the edge of the blade after 1.2 seconds? If the blade is 8 centimeters long. Now, there's a lot of fancy words in there, but tangential velocity is a fancy way of actually saying linear velocity. All right, and basically what that means, it's asking if, let's say, that edge of the blade just snapped off for some reason. I want to calculate how fast that edge is going to travel forward once it breaks off. Okay, now, linear stuff, we kind of don't have a ton of things to solve for linear motion, but we do have a particular relationship that relates linear and angular motion together. All right, and going back up here to the top of our sheet, we'll see that velocity, linear velocity, is related to angular velocity by multiplying the angular velocity by the radius of the circle. All right, so if we say v equals omega r, which is what we're looking for here, we can actually solve for this linear velocity, this v, pretty easily, because I know omega, after 1.2 seconds, it's 150 radians per second. And I know the radius is going to be 8 centimeters, because the blade is one edge of the blade is the point of rotation, the other edge is the thing going around in the circle. So the linear velocity is going to be equal to 150 radians per second times 0.08 meters, because remember, we want this in meters, not centimeters. So when you go through and multiply those two things together, you will get that the linear velocity, how fast something is moving at the edge of that blade, is 12 meters per second. All right, and we're going to find out that this is actually a very useful calculation to do, because a lot of times we'll have things that are rotating that eventually give energy. When we start talking about rotational energy and linear kinetic energy, the rotating object will give something energy, and that rotation will turn into linear motion once it's released. Okay, so with that being said, that is the first half of this note sheet. We're going to go through, and y'all are going to have a chance to kind of work through the second part more on your own, and then we'll talk about the answers. So with that being said, ladies and gentlemen, that's where we're going to stop for this particular video. The next video is going to talk about page 2. All right, so I'll see you there.